Anyway, so the outline of my talk is I'm going to talk a little bit about the science that we do at the LHC, then talk about software and computing challenges mostly in order to give you a sense of why we do what we do, and then about present solutions and a little bit about what is changing as we look towards the future. So let's start with the science. And when you're thinking about the science of the LHC, there's a whole lot of different ways that you can start this off. I like to start this off as with the dark matter conundrum, or in general, the universe content conundrum. So the universe is a rather strange place in that about 68% of its energy content is dark energy, and truth in advertising, I don't think that we really have any clue what this is. We don't even have a satisfactory hypothesis, I would argue, for what this is. Then there's another 27% of matter that is, or matter energy balance, that is dark matter. Here we at least have a whole slew of different hypotheses, but no proof of what it actually is. And if you then account for the leftovers, there's about 5% or so of the universe that we actually do understand. That is what all of atomic physics is made out of, and pretty much everything that we're used to in our daily life. And so the way I look at the LHC program, it's really all about dark matter when everything is said and done. We got our first Nobel Prize for the Higgs discovery, or meaning the theorists get their Nobel Prize for predicting the Higgs that we then discover. And now the new Higgs is dark matter, if you wish. And so to study dark matter, we'd like to create it in a laboratory. And so what I'm showing you here is the laboratory that we use to try and produce dark matter. This picture shows the Mont Blanc up on top. You see here the Lake Geneva across, and this ring here is the Large Hadron Collider, and it is underground, and I'll show you a plot in a second that shows you the tunnel. There are 4 experimental collaborations, ATLAS, CMS, LHCb, and ALICE. I'm part of the CMS collaboration, so most of my examples will be from CMS, but I would claim that whatever I talk about in the context of CMS also applies to ATLAS. LHCb and ALICE are a little bit more of boutique experiments. They have a specific focus on a subset of the total science that can be done at the LHC, and I won't be talking about that. Then if you look at the tunnel, so this shows you what the tunnel looks like. The stuff over here to the left is where the magnets are in. There's 2 beams circulating around this tunnel, and these 2 beams are coming into collision at the 4 experiments. And if you look at the LHC in numbers, it's 27 kilometers in circumference. It collides protons on protons at energies of 7, 8, 13, and hopefully eventually 14 TeV. We took for 3 years data at 7 and 8 from 2010 to 2012. Then we were down for maintenance, and we're just now starting up at 13 TeV, and we've taken about as much data now at 13 TeV as we took in 2010 at 7. There are 2,808 bunches in the machine when it's fully loaded, which means we have collisions every 25 nanoseconds, lots of protons per bunch. I have the beam size written here. And the one thing that is important for the physics of the LHC is that protons are composite objects. In other words, while we are moving around the protons in these bunches, what's actually colliding is the partons, the particles inside the proton, meaning the gluons and quarks collide, which in turn means that the z momentum of the collision is unknown, and therefore momentum conservation is used only in the transverse plane. And you'll see this, how this informs the detector building in a moment. Now, if you then step back for a second and ask yourself, what are these particle physicists doing anyway in these collisions? The way I'd like to think about it is that it's the Big Bang in the laboratory. We gain insight by colliding particles at the highest energies possible, in order to measure sort of kind of three things: production rates, what is produced at what rates, masses and lifetimes, what particles do exist, what are their masses, what are their lifetimes, in other words, spectroscopy, and then decay rates, which particle decays into what other particles and at what rate. And so from this, we then derive the spectroscopy as well as the dynamics of elementary particles. And knowing that then means that we develop a theory of nature at the smallest scale and at the highest energies and at the oldest times, earliest in the universe. And if you ask yourself, how do we make progress in this field? Progress is made by going to higher energies and going to brighter beams. Now, to give you a little bit of a sense of what's being probed, I like showing this particular slide here because it shows you double differential distribution for jet production. So on the x-axis here, you have the jet PT, and then you have different ranges in rapidity. And what you can see is that the data points shown here in black and open cover about 13 orders of magnitude. And the red line is the theoretical prediction. So CMS as an experiment, or same for Atlas, is capable of measuring making science measurements across a dynamic range of 13 orders of magnitude, and the theory predicts that those measurements to a pretty damn good degree. And apart from measuring what is predicted, there is also always the obligatory sci-fi buff slide that one might want to show. And that is, if you imagine that our 3D world to be confined to be a 3D surface in a 4-dimensional universe, and then you'd imagine that this surface were curved, and that the 4th dimension distance is short at some locations, so that that's sort of indicated here by this little hole. Then you could imagine having space travel eventually, maybe one day, by tunneling through this 4th dimension, and voila, you get the kind of stuff that you read about or see in movies, in sci-fi movies. And so how does this relate to the LHC? The LHC is searching for evidence of dimensions of space other than the 3 that we're used to, plus time. And so there are very specific observables that would be an unambiguous signal of the existence of such additional dimensions of space. And that's about as far as I want to go with discussing those details. So the bottom line of the science here is, and my recap of the science is that during 2010 to 12 data taking period, the beams crossed in the Atlas and CMS detectors at a rate of 20 megahertz. Each crossing contained about 10 protons on average colliding with each other. And so when we're talking about the cutting edge science at the LHC, we're looking for rare events that are expected to occur in roughly 1 in a lot of zeros collisions. Meaning this is sort of the quintessential needle in a haystack problem for the second running period that starts more or less now. For the next 3 years, the beam crossing rate is doubled to 40 megahertz, and we will have about 30 collisions and per crossing. In other words, we're trying to create more collisions in order to reach higher energy, higher masses, and rarer phenomena. So much for the science. That gets me to software and computing challenges. And by software and computing challenges, I would like to start by showing you a little bit what the experiment looks like. So this is the CMS experiment from the side. It's essentially a cylinder. And what you see here is with the experiment, once you take off the end cap, meaning it's you split open the cylinder and look inside. And you can see here there's a person to give you a sense of scale. And then the innermost part here is a silicon tracker. and that makes up most of the channel count. And then going outwards, you have different types of detectors that measure different aspects of these collisions. And the message from this picture, as is pretty obvious, I think, is this is a house full of the electronics in order to detect these collisions. If you then think about, again, here is the same picture, but with the end caps closed and with a person here to scale. If you then think about the CMS experiment by numbers, the CMS experiment has 80 million electronic channels. If you take the reasonable assumption that each channel gets digitized into 4 bytes, and that we're taking 40 megahertz of collision rates, then and you multiply these three numbers together, you get something like 10 petabytes per second of information. Now, as probably obvious to everybody in the audience, 10 petabytes per second of information is not something that is any technology today makes it worth storing. So how do we handle this? We have about a factor 1,000 zero suppression, meaning only 1 in 1,000 channels of these 80 million electronic channels has something in it that is worth preserving at any given moment and for any collision. And then we have about 1 in 10 to the 5 online event filtering. And the combination of this means that, and the running time per year, means that we have about 1 to 10 petabytes of raw data per year written to tape, not counting simulations. In addition, in order to understand the resolution function of this detector and calculate acceptances and so forth, we typically produce about 2.5 times as much simulation as we have data from the detector. The collaboration of the CMS experiment comprises about 2,000 scientists across 180 institutions in 40 countries. So this beast is a truly global collaboration. The CMS stands for compact muon solenoid. So an experiment of this size here is considered compact. It's the fat little guy as compared to Atlas being the big light guy, meaning CMS is heavier but smaller than Atlas. Now, if you then visualize a collision, then you may get something like this. So what you should think of is that as you can see, there's a cylinder here. The protons come in, the beams come in on the central axis of the cylinder. You have a collision in the center, and then shit flies around in all directions, basically. And this particular event is a Higgs to gamma gamma candidate, meaning Higgs to 2 photons. You can see the 2 photons in these red things, and all of this other junk is the underlying event, meaning the remnants of the proton on collision. So this would be a very interesting event that is Nobel Prize worthy, so to speak, because after all, the Higgs discovery got somebody a Nobel Prize. And this here is, in contrast, a very busy event. So what have I done here? This is a 3-dimensional view of the visualizing the experiment. This is an RZ view only. So in central here is the beam axis. And what you see here, and it's heavily zoomed in, the radius here is maybe the first few centimeters. And what you see in here is all of these yellow dots are collisions. In this event, we have reconstructed, this is a real data event, we've reconstructed 70 plus collisions, if I remember correctly. And all of these green things are charged particles that were reconstructed in order to then point back to these collisions. So as you can imagine, this is a major pattern recognition problem, because all we see is hits on silicon layers, and then we have to reconstruct those hits into tracks, and then those tracks into vertices, and so forth. If you then look at how do we sociologically function, I've put here 2 plots in order to give you a sense of activity or a measure of the number of active scientists in CMS. The plot to the left is the number of people who actively do large-scale data analysis in any given week. In other words, the number of people counted that have submitted workflows to the grid infrastructure that I'll talk about in a moment in a given week on average. And you can see that this goes all over the map, but it's in ranges from about 5 to 40% of the entire collaboration. Then the plot on the right tells you how many people have committed source code that make it into a release. In other words, it's the core reconstruction of the data. How many contributors do you have to this as a function of time? And I'd say about a quarter of the collaboration, scientists, engineers contributed to the common source code, which comprises about 3.6 million C++ log. Finally, so clearly from these two plots, you get a sense of scale. Lots of people are involved. Finally, another way to look at get a sense of scale is time. This here gives you an already slightly outdated sense of evolution of the program. We started out with run 1 at a maximum of 8 TeV. That ended in 2013. Then sometime mid-2015, we started run 2 around here, and that's now supposed to end at 2018. And then somewhere in the far future, in 2025, we will have the final run of the program. And in between, there are shutdowns to do maintenance. And the event rates, initially, we started with 150 hertz data taken to tape. Now we're planning on 1,000 hertz, and we're just starting to do that. And then somewhere in the far future, in 2025, we're considering writing 10,000 hertz to tape. And so having taken all of this in, what are the real challenges? I like to think of the challenges as how do we organize the processing of tens to thousands of petabytes of data by a globally distributed community of scientists, and do so with manageable change costs for a period of 35 years. Because if you think about it, we started commissioning the computing infrastructure in about 2005, 2004, thereabouts, and we will probably stop data taking in 2035 and then continue analyzing that data that was taken for another 5 years or so. And that gives you that 2040. So that is a lifespan of this experiment of doing science with it of 35 years. It's about the same lifespan of, almost the lifespan of an entire scientist's active life, barely more than 35 years. And so in order to do this or meet this challenge, what are the guiding principles for solutions? The guiding principle is that we choose technical solutions that allow computing resources as distributed as human resources. In other words, we want to support a distributed ownership and control within a global single sign-on security context, and we design for heterogeneity and adaptability both in a given moment in time as well as versus time. And I think that there's one thing that is really important to remember here. It's this distributed human resources. If you ask yourself what dominates the operations cost of these experiments, I claim that the operations cost of the experiment is dominated by personnel cost. Because if you count the total number of people involved, give or take, in the LHC program, it's numbers of the order 10,000 scientists. If you take $100,000 annual salary, give or take, average over the world, over the different countries in the world, that's a hell of a lot of money and outstrips anything else in terms of costs for just maintenance and operations costs. And if this is your dominant cost, then you have to design around making people effective. And I think that's really what drives the present solutions and also solutions in the future. So present solutions, before I can tell you how we solve this, there's a couple more things that I want to talk about, and that is principles of cooperation and competition. And it's important to understand, in order to understand how these experiments function, it's important to understand how they organize themselves. Each collaboration shares responsibility, and each collaboration has certain things where they fiercely compete within the collaboration against each other. So there is an intermix of shared responsibility and collaborating and fierce competing, and both modes of human endeavor, or whatever you want to call it, have to be supported by the computational infrastructure. The shared responsibilities cover construction, maintenance, creation of all primary data samples. We create the primary data for all of us, and then everybody and their brother and sister gets to have a chance to kick the tires and do whatever they want with this data. And we then, when they come back with a result of competing against each other, we then review all the results prior to making them public in order to ascertain a quality control. And in between these steps of having the primary data sample and making something public, chaos breaks loose and everybody competes against everybody else for whatever is the hottest thing in science at the moment, or whatever they happen to choose to focus on. And that then brings to it a matter of competition, and we need to design a system to allow that. And so in addition to shared resources, groups within also have private resources, and they produce private data, and that needs to be stored and analyzed in groups ranging from individual PIs or individual grad students, for that matter, to groups of tens of collaborators. Typically, a publication of a lot of publications have sort of in the neighborhood of 10 people associated to it who actually do their data analysis. And then if you look at the totality between the 4 experiments, there's about 1,000 published papers at this point. CMS alone has about 350 maybe. I haven't looked recently, but that's about this size. If I were to judge based on the things that I've seen in the collaboration, I would argue that somewhere between 400 and 400 terabytes of private data is utilized to write a paper. And that sort of sets the scale. And so then if you look at what you want to, what the software performance characteristics are for the analysis in order to define the boundary conditions of what gets done in computing, you have a production of shared data that is heavily CPU limited. It's dominated by pattern recognition of turning the detector signals, the electronic channels, into physics objects. And then there it's likely to benefit from many core architectures in the future, and we're heavily working on this. And then the production of private data from the public data is still often CPU limited. And finally, the analysis of private data tends to be IO limited. And the reason why I'm pointing this out is because personally, I firmly believe that as we move towards the future, the production of the shared data will become ever more heavily CPU limited, and the analysis of the private data will become ever more heavily IO limited. And it is not obvious to me that what we do today in terms of having one infrastructure that serves all applications is something that is going to work in the future. And you can ask me about what I think is going to happen if you want later. I just want to point out that it's very diverse today already. It's going to get more diverse in the future. Then how is it organized? It's organized via the worldwide LHC computing grid. And the key point in my mind is that the WLCG is a federation of national infrastructures. And in the USA, the national infrastructure is the Open Science Grid. And a colleague of mine told me this sort of amusing little tidbit, which is that among the top 500 supercomputers, there are only 2 that are bigger when measured by power consumptions. It's another little amusing factoid. And then in addition to this shared infrastructure on the grid, we have what we call Tier 3 centers. Those are locally controlled resources not pledged to any of the 4 collaborations. It's largely clusters at major research universities that are time-shared, or small clusters inside departments and individual research groups. And part of the design criteria, at least in my mind, for the entire globally distributed system is that it is easy to plug in additional resources that anybody in the collaboration owns. And therefore, it is easy to support the APIs that exist, and it is as important to make it easy to work around APIs that are not supported by whatever cluster you happen to have access to. In other words, you want to be able to add additional resources in order to add yourself a competitive advantage against your competitors in your same experiment. Now, how is this done in the big picture concept? I like to think of it as the me, my friends, the anonymous as a grid or cloud concept. And the way I think about this is that there's lots of users, wide breadth of users, and almost as wide breadth of clusters, if you wish, and then a small number of support organizations that provide the bottleneck to have the users meet the sites. In other words, if I'm a site operator, I don't want to know about the 10 to the 4 users. I want to know about a few organizations that then deal with the user support. And so this boils down to that you have a thin client at the user end, you have a thin API at the system end, and a thick VO middleware layer in order to support the user. And that thick middleware layer is supported by my friends, the people that I work with, the collaboration that I'm part of. And to give you a little bit of a sense of the types of services that my friends operate for me, there is dynamic resource provisioning. I want to dynamically find resources in the world that can be used in order to get my science done. There is the workload management, meaning the scheduling resources, the establishing runtime environment, the execution workload, There's a whole lot of stuff that has to happen so that my executable can run in an environment that gets dynamically provisioned. And then there's the entire question of data distribution and access, the input handling, the output handling, the metadata, the finding where is the data that I want to analyze, the moving around of either the executable or the data, and ultimately a file call log of the things that I may want to analyze in first place so that I can figure out what's there and so forth. And that pretty much covers most of what we do. There's one more aspect that I personally find important to touch upon, and that is how do we actually structure how do we organize the data internally? And this is something that I have not seen elsewhere, and therefore I want to talk a little bit about it and give you a rationale for. And this is that we actually structure our data for optimized read performance. That means that if you think about for a second what the basic challenge is, our data comes out of a detector. When it comes out of the detector, it gets processed by a software release. When it comes out of that processing, it shall never change. We want to make damn sure that I have a stable release of my data, because when I compare with my friends or my competitors, I must have some amount of guarantees. But that also means that I can design the format with the science knowledge that I have about what I'm trying to do with this data. I can therefore design the format of the data in such a way that it is fast to read, because I'm going to write it once and going to read it many times. And there's much less writing than reading in the entire life cycle of the data. And we do this by putting together information of multiple events into buckets, and so that you can pick up a bucket based on, get a collection of objects, make a selection based on that collection of objects, and then not bother reading the rest, because the rest may be irrelevant, because you're not looking for that stuff. You're looking for something else. And so you select out, filter out events fast by virtue of having a format that supports this. And now, what's the proof that this actually works? The proof that this works is this plot here. This plot shows the statistics of 23 million files read via the wide area network. And I'll show you in a moment how that gets done, reading via the wide area network. From January 2012 to February 2014, so 20 months. During that period, we read a totality of 12 petabytes. And what you see here on the x-axis is the fraction of the file that was actually read by the application. And on the y-axis, it is how often you have files where this fraction was read. And then if you look at this, if you analyze this thing, you find that the median is at 8.5%, meaning 50% of all files in these 20 months were only 8.5% of the file was read. In other words, somewhere we're doing something right in defining our data format in order to make it efficient for reads and to minimize I/O, basically. The other thing that you see is that there's an overflow bin here, meaning some of the times we screw up and we read more than what is actually in the file, meaning we jump back and forth in such a way that the reading is inefficient. And there's a whole story to this, of course. Anyway, I won't bore you with our dirty laundry. Then walking towards future solutions. So where do we go from here to the future? If I wanted to describe the past, I guess it really is the past because the future has already started. Initially, we operated a largely static system. Data was placed quasi-static before it can be analyzed. In other words, we had a data placement system that anybody in the collaboration could request data placement in any location in the experiment. And an analysis center had to have a contractual agreement with the collaboration. And that means, and all centers were known, they had to be part of this data placement regime. All reconstruction is done at centers with these custodial archives. And you couldn't do anything until the entire data set was placed, and while data was in transit, it was not analyzable. So that led to, that was designed, first of all, to make it simple. And it was designed around the notion that wide area network transfers are, the world has little experience with, and especially at our scales. And in fact, we spent about 1.5 to 2 years just debugging the total mesh of wide area network transfers relevant to our experiment. And this was a multiple FTE year effort. So in the beginning, it was indeed true that moving terabytes around across the world was a non-trivial undertaking. After we had debugged this system, this global system, nowadays it has become de facto workable, and we basically stopped thinking about it. And so now we're much more willing to do things dynamically, and as it turns out, this is increasingly also necessary because we have too much data to afford this kind of static system, especially given disk prices, commodity disk prices going up relative to, or just to give you a sense, I operate one of these tier 2 centers in San Diego. I used to hypothesize that about 10 to 15, maybe 20% of my budget goes into disk. Today, 50% of my budget goes into disk, simply because Moore's law in CPU has been much more kind to us than Moore's law in storage. As we look towards the future, dynamic data placement is being done, meaning data is placed at tier 2s based on job backlog in the global queues. Then we do wider network access. We call this any data, anytime, anywhere. That means that jobs that start on the same continent as data instead on the same cluster as data are allowed. Data is cached in additional local clusters while it is read via the wider network. We have developed a global data federation. In our global data federation right now, there is more than 100 petabytes of disk space. We use that essentially you can read from anywhere to anywhere. De facto, our user community has learned the hard way that it doesn't make much sense to read across the Atlantic. You are better off sticking to one or the other side of the Atlantic due to latency issues. Then finally, we have the dynamic creation of data processing centers meaning we are starting to elastically scale out to support peak needs. You can look at this as a positive or as that is generally useful, or you can look at it as a response to our inability as a collective to produce releases on time. Either way is a viable way of looking at it. Essentially, when it takes a long time to make a software release that is worthwhile and validated to reprocess our data, given that reprocessing of our data is a very costly undertaking. As a result, but when we have it finally done, we're in a hurry and want to get our data processed ASAP, and therefore it would make much more sense for our operations to scale out when the release is ready rather than have steady state operations. It just is, for the science, much better. In addition, the dynamic creation also involves agile use and sharing of more diverse set of resources. That speaks back to the competition factor. I have a slide here on how any data, anytime, anywhere works. The basic idea is that the user application talks to a centralized redirector. There are multiple such redirectors. In fact, what it ends up happening is that there is a tree of servers, and at any branch of the tree, a user could connect to. What then happens is at that branch downwards, there is a protocol that searches for a file downwards from the tree. If it doesn't find the file downwards from the tree, it sends the request upwards in the tree, and you can therefore figure out where the actual file, where the server is that can open the file for you. Then you get redirected to that server, and you open the file, read the file, voila, happily ever after. And this is done in such a way that we even have a multi-source protocol. In other words, the application itself has the ability to say, okay, fine, let's try out a new guy, an additional source, because and just see whether any of the other sources of this file is performing better than the sources that I'm personally using. And so there is an algorithmic way of learning about additional sources while the job is running, and switching between sources for where the files are read from. Then the other thing that I wanted, let me make one more comment here. The other thing that is probably obvious to those of you who've dealt with I/O issues before, for something like this to make any sense, you have to have an I/O layer that is largely latency tolerant. What I mean by this is that if your application asks for a byte at a time and always waits for that byte to arrive and then asks for the next byte, you could never read across thousands of miles because the finiteness of the speed of light would kill you. And so we've designed our I/O layer to be as latency tolerant as possible, and that in its own right is actually a non-trivial technical feat. And I can point you to literature on that if you're interested. So then the other thing that I wanted to mention is the vision going forward. This goes back to my elastic scale out. The vision is that raw data comes from the detector at CERN. It gets stored at tape archives in national labs like Fermilab in the US. The similarly simulated data gets produced in the cloud or on OSG or on whatever resources are available and stored at the archive at the national lab. Then there is some amount of steady state processing as the raw data runs in. And then there's some amount of peak processing of data that needs to be reprocessed. And that peak processing happens at additional centers like SDSC or Amazon or fill in the blanks, whatever resource we can get our grubby fingers on. Finally, the data analysis largely happens at what we call tier 2 centers, or tier 3 centers, basically centers that are under the control of the end user scientists or at universities in various ways of degrees. That brings me to my conclusion, to give you some time to ask some questions. Summary and conclusions, what we do, I would think of guided by a few very simple principles. We want to support distributed ownership and control in a global single sign-on security context. We want to design for heterogeneity and adaptability, both today, heterogeneity across infrastructures, and adaptability towards change as we look towards the future. And then we want to submit locally and compute globally. In other words, in order to maximize the effectiveness of our human capital, we want to be able to, for people to work on their desktops, local clusters, labs, laptops, where they have complete control and do something interactively there, develop source code, try source code out, access raw data or process data from their interactive platforms, irrespective of where it is located, and then submit for large-scale processing and do the large-scale heavy lifting globally via whatever resources that are available, and bring back the results to whatever location the end user has access to, the scientist has access to. I would claim that the LHC experiments are very successful, have very successfully implemented these kinds of ideas in order to deal with our big data. And looking towards the future, the main challenge that I see is that this originally largely static system is becoming more agile and more elastic. We will be seeing more heterogeneity in the future. I firmly believe that we will be seeing, we will have to be able to use different computer architecture, that it's not all x86 anymore in the future. We will have, we will use some of our types of applications only on certain architectures because they are more effective for the specific things that we do. This means that we will have to figure out how to make all this work. And that's where I see the challenges. Thank you very much.